All right, before we talked about if we were looking at velocity, and the easiest case where velocity is always positive or greater than or equal to 0 even, the fact that we're always going in the same direction, we can talk about finding distance traveled. And we talked about distance traveled is area under the curve. And when I say under, I really mean between the curve and the x-axis. So that we're going to expand on that as time goes on about this. Now, velocity is a rate of change. It's a rate of change of position. Position on the highway, position of a ball in the air, that's the rate of change of position. So the distance traveled is our total change in position in the amount of time. And I should do from, say, t equals a to t equals b. And what we can do is we can generalize this to any rate of change. So let me write this down. Velocity is a rate of change of position. And what we can do is talk about any sort of rate of change. We can, if we have a rate of change of a population, then the total change of the population from a certain time would be the area under the curve. If we have a rate of change of our cost, it will be area under the curve. So let's look at an example. If we're looking at a population change changes at a rate, and I should say grows even, at a rate of 50 per year. Looks like I'm going to need some new markers. And when we do this, when the rate is constant, if we're looking at from year 10 to 14, we want to be looking at what is our total change in population. And when we think about this, when it's constant, just like when we were talking about velocity being constant, when we look at this, so for 50 per year for 4 years, we know that it changes, in this case grows, by a total of 200. 50 times 4. And that's really what we're doing, is we're doing area under the curve again. In the sense that we have 50, we're going from 10 to 14 to get the area to be 200. So we have width 4, height 50. The total change in population in that amount of time was 200. And when we're not constant, we have the same idea. That if our curve is some sort of rate of change, we want to be looking at area under the curve. And what we're going to do is we're going to estimate with rectangles. And estimate areas with rectangles. And this is called the Riemann sums. There's a fancy term for this in the sense that we're adding up, we're summing up a bunch of rectangles to estimate area under the curve. So let's look at an example. In this example, we're given a function negative 3x squared plus 50, and that's representing a population change of, say, a bacteria, where when x equals 0 is when we introduced an antibiotic, and so the population change went down. And we want to know from 0 to 4 hours, how much did the bacteria population change by total. And so that would be the area under the curve. Now, if we just use 2 rectangles, that's a pretty crude approximation. And we can change using different endpoints. So this one is using left endpoints. So we have it split into 2, and we have use the left endpoint for our height from 0 to 2, and then our second interval is from 2 to 4. That's where our second rectangle is, and so we use the left endpoint to determine the height. And so when we do that, we get width is 2, height is 50. In this case, width is 2 and height is, I think it ends up being something like 37, something like that, or 38 actually. And then we add those up. The bigger n is, the better the approximation is. So to do it by hand, it would be really tedious. But as n grows, we can barely tell the difference between the areas of the rectangle and the area under the curve. And what we do is we look at this is fancy notation for the adding up all the areas of these rectangles, and we see a pattern like we did with velocities in chapter 2. Do we see a pattern of these numbers? And it looks like it might be getting close to maybe 136, 136.5, hard to say. So if we change to a different type of rectangle, using the right sums instead, those in this case are underestimates, and those are getting closer, a little bit below 136. So we might think that the actual area under the curve is 136. And what we're going to do is we're going to find better ways to do this than to do this with Riemann sums and areas of rectangles.